Right, it looks we are online. Hello, everyone. Welcome to Astronomy on Tap. This is the nth version. I don't remember anymore. It's been too long in Longtown. As usual, Astronomy on Tap is bringing to your home, your sofa, your bed. It looks we are online. Sorry, I have the feedback sound from my own voice. It's very weird. And so we're bringing to you astronomy on your sofa, on your couch, on your bed. So please relax. Usually we would meet in a pub, so we encourage you to get some drinks, to get some snacks. So this is very informal. And today we will be talking about exoplanets, and we'll specifically be talking about, for once, things that you can actually do in a lab with astronomy, which is quite it's not, we can't do that for most of us. We have to rely on telescopes and simulations mostly. So it's very exciting. And I think I will pass on to Chiara for introducing the speaker. And we have also a few questions that we've been asking throughout the week on social media, and I will repost them on the chat, and you can try to think about them while Clark will be giving his talk, and you can try answer before he does. Right, 3 points to whoever answered the questions before he does. Okay, Chiara.
Yeah, thank you, Roman. Hi, everyone. So our speaker today is Clark Baker. Hi, Clark. Welcome. He's a PhD student at the Queen Mary University of London. And as also Roman said, it's very exciting today to have an astronomer who is actually working in the lab. So Clark, do you have any highlights about facts that happened at work?
Yeah, so I have a little story. Essentially, one of the dreams I have is to go and observe in one of the big telescopes in a facility like the ones you see in Hawaii. And so I don't know if you know the saying, dress for the job you want, not the one you have. So I started on Fridays to wear Hawaiian shirts, and I thought this was good, a little dress down Friday in the office. And people started to give me funny looks, and they thought, why is this guy wearing all these very loud shirts on Fridays? And so eventually they built up the courage and they came to me and they said, Clark, why are you wearing Hawaiian shirts? And I said, well, haven't you heard the news? It's Hawaiian Shirt Friday. So slowly the news got out and people started to join in. And eventually we got more and more people to wear Hawaiian shirts on a Friday just from leading by example. And then finally, it essentially culminated in one of the proudest moments of my academic career so far, which is this brilliant image. So I haven't made it to Hawaii yet, but I think this is probably just as good.
Very cool. So yeah, once you're ready to go to Hawaii, then all the group has already the Hawaiian shirts.
Exactly. We're ready.
Great, thank you. Yeah, and then I'm going to quickly read the questions. Clark will give the answer in the talk, so be careful and pay attention. But then we'll discuss again the answers after. So the first question is, how big does a telescope need to be to take a picture of an exoplanet? The second question is, what does an ambulance siren have in common with starlight? And the third question is, what is our current cutting-edge technical limit to exoplanet discovery?
Excellent. Right, I'll take it away then.
Yeah, I'm jealous of your Hawaiian shirt collection. I have to say, I've been to Hawaii many times, and I have no Hawaiian shirts.
Oh dear!
I've missed something there. It's yeah.
You should work on that.
Yeah.
Okay then. So I'm going to be talking to us today about exoplanets and the interstellar game of hide and seek. So we're going to start off by talking about some of the planets that we have found already and what maybe could still be out there. So this is a graph you'll see a lot in my field. It's a plot of the period of the orbit of the planet against the mass of the planet. And we break down this field into several different categories of planets. So we have classical giants, something like we see in our own solar system with Jupiter, all those sorts of planets. hot Jupiters, we have warm Neptunes, super Earths, and rocky planets. But something you may be missing on this graph is where is our Earth? So that would be down here. So you might notice there's not really so many data points around the area, and that's because with our current technology, it's very, very difficult to detect an Earth-like planet around a sun-like star. So if it's so hard, why are we so interested in doing it? And this is kind of what I'm going to talk about now. There's a thing called the habitable zone, which is a terminology which essentially states a region around a star where you're far enough away that liquid water can exist on the surface of the planet, but you're not so far away that it's ice. And so for different stars, this is a different distance away depending on the size and the intensity of the light from the star. And you can see on the top there where our Earth sits perfectly in the habitable zone. Now, we call it the habitable zone, but it doesn't necessarily say anything about how habitable the planet is. It just says that liquid water can exist. It doesn't say that you could go there and breathe and you'd be fine to live on the surface of the planet. And then there's another criteria. So in 2015, there was a paper that released that was talking about these amino acids, these 20 amino acids that we think are required for life to come about and to form. And essentially for this prebiotic chemistry to occur, you need a certain amount of UV light incident on the surface of the planet for these reactions to take place. And so in 2018, there was a paper that went through and looked at the overlap between the habitable zone, so where you're going to have liquid water on the planet, and also you're going to have enough UV light for this prebiotic chemistry that could form life to occur. And you'll see in the top right-hand side there that the Earth is sitting in that region, as we would hope, because we have life and we have liquid water on our surface, but there's not really much else there. If we want to start looking for life around exoplanets, this is kind of the situation we want to look for, is Earth-like planets around sun-like stars. So how do we go about doing this? What seeking strategies do we have? So we know these are quite good seeking strategies because we found over 4,000 exoplanets with them so far. And I'm going to talk about two of them now. So direct imaging, this one is probably the simplest to think about, but one of the hardest to do in practice. So imagine you want to take a picture of an exoplanet system, like you see here with your planets and your star in the middle. So you point your telescope at the system and then you take some pictures. And then if you've got everything in place, you get these nice images, and then you can work out, you can see sort of the orbits of the system, and you can get sort of, this is the one observation where you really get to see the detailed orbital information. And then from the temperature of the star, you can begin to work out things like the mass of the possible planets. But it's not quite so simple as just pointing your telescope and taking these pictures. In fact, there's a number of issues which can get in your way. So let's say you've got a ground-based telescope. You want to go and take your pictures of whatever you're taking pictures. Let's say you're taking a picture of Jupiter in our own solar system. And you might think, oh, I can take this nice clear picture like we see here. But in fact, actually what you're going to get is this. It's going to be all blurry if you're in a place with bad seeing, as we call it. So this thing called atmospheric seeing is as light passes through the atmosphere of the Earth, the turbulence in the atmosphere will distort the wavefronts of the light, and essentially you will blur your image. So we need some clever techniques to try and get around this. First of all, the obvious thing is to try and build your telescope somewhere where there's less turbulent atmosphere less of the time, so you'll have better seeing. Secondly, there's a very clever technique which was first brought about by Horace Babcock in 1953, and he proposed that essentially you measure the distortions caused by the atmosphere, and then you use something like a deformable mirror, which can then basically counteract the distortions and give you your nice clear image as you would like. This didn't come into fruition really until the 90s, when computer technology was good enough to measure these deformations and control these mirrors. So you've got your system. You can now take nice clear pictures, and you point your telescope up at your planetary system that you want to take your images. So you take your picture, and then out you get this, just a big blob where the star is. It's nice and bright. So essentially, what's happening there is that the sun is so much, the star is so much brighter than the planets that the planetary light is buried within all of this starlight. So we need to remove the starlight somehow. And the way we go about doing that is using something called a coronagraph. So this was first invented in 1931 by Liat, and he proposed that we place a mask in the optical system, which then would block off the starlight and then leave behind the planetary image. Unfortunately, some of the light will get through in this system. It's been refined over many, many years, and they're very, very good now at blocking starlight. And excitingly, some of the sort of newer techniques use things called phase plates, which you place in the optical system, and they interfere with the starlight, and so they deconstructively bring about these things called dark holes. So they essentially remove the starlight from the image at your focal plane. So we've got rid of the starlight. We want to go and take our image of the planets now. So you might hope that you'd be able to get an image like this, something that you would see in sort of like a press release for an exoplanet. Unfortunately, these are just artist impressions. And in fact, what you're actually going to get is just a blob of a few pixels, an unresolved blob of light. This is because of an effect called diffraction. So essentially, your telescope has a physical size, it has a physical aperture. And the larger your aperture, the higher the resolution of the image you can achieve. Unfortunately, though, we can only build telescopes of certain aperture sizes. So we can't, let's say we wanted to take our nice, let's say a 4 megapixel picture of an exoplanet. In order to do that around Proxima Centauri, so if we had the Earth orbiting around Proxima Centauri, which is the closest star to our sun, which has an exoplanet around it that we've detected. And you would have to have a telescope essentially with the aperture size of the Earth, which is currently, with current engineering, we can't build something of that size, but maybe that's left for future generations. But we do get these nice blobs, and these blobs are still fantastic because, as I say, you can get orbital information, you can do all sorts of things to try and characterize the planets in this way. So that's great, but it doesn't tell us the full story. We need to then, sort of the big bottleneck here is these coronagraphs and how well we can remove the starlight. So with current technologies, we're able to get down to planet-star contrast ratios of 10 to the minus 5. So that means we can look at planets which are orbiting around stars that are about 10,000 times brighter than they are. So we can look at sun-like, so we can look at large planets around sun-like stars, but we can't currently look for an Earth-like planet around a sun-like star, which would require us to get down to contrast ratios of 10 to the minus 10, so 10 billion, which is one of the big pushes at the moment. So that's the first technique. Now let's talk about our second technique for this talk, and that's the Doppler method. So essentially you have your planet orbiting around your star, and both of them orbit around their center of mass. And so then that causes the star to wobble. As it comes towards us, the light is blue shifted, and as it comes away, it's red shifted. So if you think of the ambulance going past, and you can hear the siren as it passes you, change in pitch, it's essentially the exact same physical phenomena. And from this, we can work out the minimum mass of the planets, and also we can sort of look at orbital characteristics of the planets, period, those sorts of things. How do we go about doing this? We design these very high resolution, highly stable spectrometer systems, which then break down all of the spectral lines, all of the colors coming from the star. And then we watch how these spectral lines move. So you see on the right-hand side, we have this plot, and it shows how one of the spectral lines from a star is moving as it moves away and towards us. This is heavily exaggerated. This is for 1,000 meters per second rate of velocity. We're more thinking about something like this. So very, very tiny movements, and maybe even 10 times less than this if we're looking for the type of planets I'm talking about later on. So these systems are extremely sensitive. I'm working on a system at Queen Mary, one of these spectrometers, and when it's not stabilized, if you tap on the desk, you can physically watch the spectral lines moving from side to side. And in fact, it's so sensitive that you can actually measure the timetable of the London Underground underneath our office with the spectrometer system. How do we get rid of these oscillations that we don't want to see? How do we just want to measure the starlight? We don't want to measure the London Underground. So we build these temperature control and pressure control systems. And so we essentially nest them in these boxes, getting down to very, very high precision stability on temperature and pressure. And with all these things, we're able to achieve, we're currently achieving 50 centimeters per second precision. And to get down to sort of the Earth orbiting the sun, we need to get down to sort of 9 centimeters per second. So there's a little way to go, but we're getting there. So with Espresso coming online recently, that's aiming for sort of this 10 centimeters per second, and HARPS 3, which is an upcoming instrument, that's also trying to get down to 10 centimeters per second precision. So very soon we will be in the region where we can start looking at Earth-like planets around sun-like stars with Doppler spectroscopy. And then next up with imaging, in this sort of future, the NASA decadal missions which are being planned, there's HabEx and LUVOIR, which are competing, and they're aiming to build high contrast imaging systems that can get us down to the 10 to the minus 10 imaging. But this is a long way off yet. These technologies still need to be studied more. But something that we can do in the meantime that I'm interested in is that you can combine both spectroscopy, which can get down to the 10 to the minus 5, and imaging, which can get down to the 10 to the minus 5. And then together you can get the 10 to the minus 10 that you need to search for exoplanets, Earth-like planets around sun-like stars. And so there's a paper in 2016 that discussed this. And what it says is, instead of placing a CCD on your image pane and just taking a picture of your high contrast image, you place many, many optical fibers. So each pixel is essentially you're using an optical fiber. And then from each one of these optical fibers, you then go to a separate spectrograph. And so you can use the spectrograph to separate the light from the star from the light from the planets, and then that helps you to get down to this high contrast range. The problem is with these sort of spectrograph systems, they're very expensive. You're talking to build an instrument like this. So it's just one of these spectrographs is going to be sort of it's going to be millions of pounds, and then to build an instrument like this, you're going to sort of talk about billions of pounds. And also these spectrographs are very large, sort of like the size of a car. So you need a very large facility in order to build them. So something needs to change with that. And so for my PhD, I've been working a lot on compact, low-cost spectrometer systems that can achieve comparable resolution to these large systems, but on the order of sort of 10,000 pounds and the size of a shoebox. So with that, this instrument becomes a lot more feasible. And so you could build something like this for sort of a few £1 million instead of billions. This instrument has gone very well. I tested it recently just before the lockdown, and we took some spectra from the telescope at Queen Mary, and we have some nice spectra of the moon here. This is the Earth's telluric lines. And another little project that I'm working on is a spectrograph concept for the GTC, which is a big telescope in La Palma. It's a 10-meter aperture. So currently these sort of spectrograph systems, we find them placed on 3 to 4 meter class telescopes. And so with this 10-meter aperture, we'd be able to find planets that are fainter and further away, approximately 10 times more planets possibly in our solar neighborhood. And then in terms of, we can start to characterize atmospheres of a lot more planets, possibly even 40 times more atmospheres we could characterize than we can with current size telescopes with these instruments. And then of course I couldn't give a talk like this talking about what's next without mentioning the EELT and the extremely large class of telescopes. These are going to be sort of 30 to 40 meter in aperture telescopes. And so they're going to greatly increase the fainter and further away objects that we can look at, and then also allow us to get much higher sort of signal to noise observations of exoplanet atmospheres and studies of these nature. So what sort of exciting things do I think are going to happen in the next sort of few decades? I think the technology, the instrumentation is going to get to the point where we can begin to detect these Earth-like planets around sun-like stars, and then we can start to look for biosignatures and sort of some of the things that might suggest that life are on a planet. And you may have noticed I haven't really spoken much about biosignatures in this talk, and that's because already on the channel, if you're wanting more after this talk, you can go and check out a brilliant talk about exoplanet atmospheres there. So yeah, that's me. If you have any questions, I'd be very happy to answer them.
Great. Thank you very much, Clark, for this great talk.
Thank you.
Nice overview as well of what you can do as a PhD student already. How what you can develop, and it's I think it's quite inspiring.
Yeah, thank you. It's brilliant. It's great to sort of have a play around with these sorts of things.
Yeah, and you get to touch things, which
exactly. Yeah. That's one of the things I like to sort of get up and stretch my legs after sort of sitting behind the computer for a little while. So it's good to head down to the lab and start to tinker around with some bits and pieces.
All right. So, Chiara, maybe if you stop sharing your screen, we can have everyone on the same page. So yes, to anyone who's on the chat, please start asking questions. So we have some delay, I know, for those watching, but please start asking questions. In the meantime, we'll perhaps discuss the questions. So I think you answered most of them indirectly or directly, Chiara.
Yes, maybe we can recap again the answers. So Clark, about the first question, how big does a telescope need to be to take a picture of an exoplanet?
Yes, well, actually, it doesn't really need to be so big at all if you just want to get an unresolved point image of it. But if you want to sort of start taking pictures like we think of the detailed extended objects, then you're going to have to get absolutely huge telescopes. And so the example I gave was sort of if Earth was orbiting around Proxima. So, but that's a very, very close example. The next sort of star systems are further away. It just gets harder and harder. And so eventually you're going to have to start building telescopes that would sort of stretch between the sun and the Earth before you'd be able to start taking pictures of them. So we need some new technology or very, very good engineering if we want to try and do that sort of thing.
Thanks. So about the second question, what does an ambulance siren have in common with starlight?
Yes. So this is brilliant. Like without this effect, we would have a lot less idea of sort of what was going on in the universe. But it's as the light, if an object is moving away from us, then the light gets redshifted, and if it comes towards us, it gets blue shifted, and so it's changing color. And the same thing happens with sound waves. So if you have your ambulance going past, as it passes you, it goes from coming towards you to moving away, and you hear that change in pitch. So it's always a very nice example to give.
Yeah, so it's an effect that we experience every day in real life.
Exactly.
That we exploit quite a lot in astronomy too.
Yeah.
And then the last question is, what is our current cutting edge technical limit to exoplanet discovery?
Yes, so we've seen that currently we're sort of at the very precipice of very, very soon being able to sort of find these Earth-like planets around sun-like stars, and we can start finding analogs to our own planet. I think that's very exciting. Who knows what we're going to discover when we start getting to that point. And also there's other great stuff we can sort of begin to characterize atmospheres of a lot more planets. Yeah, all in all, it's very exciting times to be in this field.
So we have a first question on are red dwarfs not better places to search for planets and life in the short term?
Yes, so we can, with current technology, we can do a lot more with red dwarfs because essentially the stars are smaller, they have less mass relative to their planets. And so then even with just the Doppler method, you can get a lot more information because essentially the planet is moving the star a lot more. And so then you can you get a much higher sort of signal observations. The issue then is that if you're looking at an Earth-like planet around a red dwarf, if that paper is to be believed, then you wouldn't be getting enough UV light for this sort of prebiotic chemistry to occur. So if that's the case, then maybe we wouldn't expect to find life on these sorts of planets. But who knows? We can always be surprised. There could be some other mechanism.
Right. Yeah, Chiara, maybe for the second question.
So the second question here is, can a high-resolution spectrometer detect the signatures for the prebiotic chemistry that is necessary for life on an exoplanet?
So it all depends on how much signal you can get in. In terms of finding those exact chemicals, I'm not fully sure, but you'd be able to look for biomarkers in the atmosphere, such as sort of methane or oxygen, these sorts of things. Some people are looking for even sort of like chlorophyll, if you want sort of plants of that nature. And so you can even look for things which suggest atmospheres similar to our own planet, such as looking for a Rayleigh scattering slope. So if you see that sort of the blue light is being scattered, that suggests that the atmosphere is similar to our own. So there's all sorts of different techniques, but whether we can, I think you'd have to have very, very, very high signal to noise to detect sort of very specific. It depends whether they're vaporized in the atmosphere and that sort of thing.
So it's actually the third question is what about the noise from the stars? And I guess it's different for every measure, for every method, right?
Exactly. So active stars, that's where things become more difficult, because let's say, for example, you're looking at a transit and you see your planet passing between you and the star. It's blocking some of the starlight, but equally you could have spots on the star, which could then also change the brightness. And so then you have to sort of begin to decouple those sorts of things. And similarly with the radial velocity, so that they can impart the star's activity can impart some radial velocity signal as well. So essentially you need to have a case where your planet signal is stronger than your star noise.
Clark, since you're an exception in the kind of speakers that we had so far, can you describe a typical day in the lab that you normally have?
Yep. So if I need to realign the system, so let's say I'm building a spectrometer system like the one I showed in the talk, and so essentially, let's talk about the day when I took it up to the telescope to test it out. So I needed to make sure everything was aligned. It hadn't moved since the last time I played around with it. So you sort of get down into the lab, you fire up your lasers and your lights that you're going to be using, and then you align the system, make sure that everything is passing through as it should be. Take some test spectra with your test sources, and then you can sort of take the spectra up to the telescope, the spectrometer up to the telescope, and then plug that in, point at your object, wait for it to get dark enough that you can start taking spectra, and then you can start taking pictures and do all that sort of fun stuff.
So do you consider yourself more, or what was your background? I wonder, is it more, is it all optics in the end? And, you sprinkle the astronomy science space on it?
No, so I did a physics degree. Yeah. And then I've always enjoyed, so my passions were sort of space and instruments. And so I sort of just put those together. I studied whenever I could pick options that I could study in undergrad. I sort of picked the space ones or the instrumentation ones. And then for my master's, I did space. I sort of specialized in space instrumentation, and so I worked on these sensors for CubeSats. And then from then, I saw the advert for a PhD in instrumentation for exoplanets, and I thought that sounds really good. And so that's how I got into it. And then I had to learn the optics along the way, because I just had sort of undergraduate physics level of optics. And so for this, I had to sort of work out all of that stuff that was going on. But it's great fun. It's the sort of work that when I'm in the lab and I'm playing around with the system I've got, it's almost like playing with a Meccano kit. So you've got to like you've got your little spanners and your screws and things, and you've got to set everything up. So it's good fun, really.
That's what it looks like in your picture where you're in the lab with your lasers and.
Exactly. They're just playing, like they're paying me to just play around, really.
Right. Yeah, there is a follow-up question actually, Chiara.
Yeah. So, do you know of any current mission which aim at better understanding the stellar noise?
And so there is I think there is, so the person precise that for the sun, so they're referring to the RV noise.
Yes.
That would make the Earth unobservable, depending on the stellar models or the instruments.
Off the top of my head, there's lots of experiments which look at the spectra from the sun, and they try and sort of decouple, and they use that as an example to try and sort of understand these noises. So you've sort of on the short term, you have granulation, and you have these sort of convections, and sort of like I say, there's the magnetic activity with the spots and things. I'm not sure of any missions that are specifically looking at the stellar noise, but I know another PhD student in my group was studying sort of modeling what the spectra of the stars would look like with different noise in them. So I'm sure there's many people. This is not my field, but this is not what I'm sort of working on. But yes, there's many people that are studying these sorts of things, especially sort of the ways that we can decouple them from the signals that we're measuring.
But I guess it's a problem of resource allocation where you want to look at the exoplanet, but you still need to invest some time taking a nice spectra of the star each time and that kind of thing, right? It's
I guess sort of whoever's going down different paths who's sort of studying these things.
But do you use the same instrument, or do you have to use two different observatories to observe the star, observe well, not in the RV case, right? But
yes. So
direct imaging, perhaps it's not the same instrument.
Yeah, with the direct imaging, you're designing an instrument specifically to get rid of light from the star. So you don't want to be looking at the star with that instrument. But yes, there's many sort of, even if we're just talking about sort of photometry, there's many instruments which are just looking at the star. And so you just there's plenty of experiments around.
So here is a final fun question for you. Has anyone found any flat exoplanets?
Well, not quite yet, but I'm sure there's plenty of flat earthers that are trying to do that. It seems kind of strange that if Earth was the only flat planet and everything else appears to be spherical, so maybe we should try and find others which could be like our own flat Earth. But
along these lines, I mean, it's still very difficult to say something else than it's probably a ball of something. Inferring the density or the density profile or even the atmosphere is quite difficult, right?
Yeah, of a flat Earth.
I mean, the thing is, if it was actually flat, could you tell? That's a real question.
I guess it would depend whether it's edge on or face on, because if it's sufficiently flat that it just passes in front of the star without blocking any light hardly, then you're not going to see it. But then if it's face on, then it will just look like a spherical planet. So that's actually proposing quite a few questions in my mind. Is actually how do we know that all of these photometric planets aren't flat and just face on? And
in direct imaging, right, you don't resolve it anyway, so it would appear like a blob anyway.
Yes,
even if it's a bit tilted. So
exactly. So
that's a fun question, I think. Of course, for anyone watching, it's all spherical. Don't start looking for flat exoplanets.
We're not going to stop you, though.
Yeah. If you build a spectrograph for this, just let us know, and Clark changes it. And
we should come and give the next talk.
Give money to this.
Yeah.
So you're at the end of, I think we didn't mention this, but you're at the very end of your PhD, right?
Yes. So I'm hoping in the next sort of week or so, I'm going to submit my thesis. So I'll be done there, and then I'm going off to do a postdoc, and I'm going to be working on quite a lot of the stuff in HARPS-3, which I mentioned a little bit. So that's a very exciting mission. It's going to have sort of 10 years of taking spectra around the stars that they want to look at. So yeah, I think it's some exciting times to come for me.
Yeah, that sounds very exciting, and we wish you the best of luck. Thank you for taking the time to talk a week before submitting your thesis.
No, it's a pleasure. It was a good break, actually. I've done enough writing. I wanted to play around with making funny slides.
And it's probably now that you have the best overview of your thesis anyway.
Oh yes, definitely. Yeah.
After that, it's going to fade away, and
exactly. You've got me in my prime right now.
Right. So thank you everyone for following. It was a bit quiet tonight, but please share the video as usual. I know people are very keen to watching and rewatching this afterwards. Next week we will stay on the topic of exoplanets, and so we have the chance to have another postdoc from UCL that will talk to us about water vapor that was found in an exoplanet last year. So you might have seen the news. It was around September or November, I don't remember, 2019. And they found water vapor in a planet that is in the habitable zone. And it's, well, I don't want to spoil it, but it's not habitable, as you can read from the news, because it's probably a giant gaseous planet. So you can have water. It's probably vapory or maybe even liquid, but well, there is nowhere where you can sit. But it's prime. It's a first, and on top of this was a big thing in the news at the time. There were two teams that were competing for the same results, and they published within a few hours of each. So there is also a nice little story about this, and I'm sure we'll talk about this next week. So yeah, please tune in, and we'll talk again about actually, now that we have the instruments, and Clark has told us how to build these instruments, we'll talk about how we go about using them. Yeah, that's it. Don't forget, you can follow us on Twitter, Facebook, Instagram, the YouTube channel. It's also the best way to get alerts for the next video. And if you are an astronomer, astrophysicist based in London or around, because at this time it does not really matter, please send us an email, a direct message, or whatever. We'll be very happy to host you here at some point. Thank you very much. Thank you, Clark, again.
Excellent. Thank you for having me.
Thank you, Clark. Bye, everyone.
Bye.
Bye.